In this lesson we see an interesting problem, which is the intersection of two linear subspaces. The idea of the intersection, as you know, is to find those vectors common to all subspaces that we are considering. Interesting of this new method, is that we use our orthogonalization algorithm. We will be able to see the concept of intersection, in a very different way. It's as if we could put some special glasses, that allow us to see the world of algebra, the world of the intersection of subspaces, in a different way, and this will enrich you. So, we have prepared this transparency, and we have written the intersection of two subspaces S1 and S2, in three different ways. The first is the usual, with S1 intersection with S2, what you're saying is that we look for the elements common to both, to those two subspaces S1 and S2. In the second part, what we have done has been to change subspace S2 by the orthogonal of its orthogonal, and the orthogonal of a orthogonal is a subspace, which is the initial subspace. Therefore, we change nothing if S2 is replaced by the orthogonal of its orthogonal, that is, we are putting back S2. The third alternative, is to make the same with S1, that is, if the subspace S1 is represented as the orthogonal of S1, we are change nothing. Therefore, we are seeing the concept of intersection of subspaces, of three different ways, according to the three expressions. Let's analyze what you have there, in the transparency, in a certain detail. The first one, is reflecting the traditional meaning of intersection, which are the common elements or common vectors of the two subspaces, and in the second, we is saying that the intersection of two subspaces is the orthogonal subspace to the orthogonal of S2 and S1. This is important, it's another way of looking at that intersection. Of course, the third version is the subspace orthogonal to the orthogonal of S1 and S2, and this is also important, because these versions, apart from giving us different visions, they are telling us how to calculate the intersection subspace. They are giving us a new and original way of calculating the intersection, and the idea is very simple. For example, in version 2, the subspace orthogonal to the orthogonal of S2 and S1, we are saying that first, we have to calculate the orthogonal subspace to S2 and, once we have calculated that subspace, we will have to calculate the orthogonal of that new subspace, but in S1. So, let's give an example, to clarify the required steps. In fact, we will put two examples. In the first example, we want to obtain the intersection of two subspaces that we are giving in the L form of a list of vector generators, where the L represents the linear combinations of those vectors. Therefore, S1 is a subspace generated by those two vectors, that you have there, the 1 0 - 1 0 1, and the 0 1 1 1 1, and the subspace S2 is given also in an analogous form, that is, it is the subspace generated by the vectors 1 - 1 - 2 - 1 0, and 0 0 1 1 0. So that the thing is clear, we are going to get this intersection, in two ways, and we will check that we get the same subspace. The first, is the version you have there, with which we have to first, calculate the orthogonal of S2, and then the orthogonal of that in S1. Now let's start by this process to get the orthogonal of S2. You already know that it is very simple, you have to enter the generators of the subspace S2. In this case, they are the 1 - 1 - 2 - 1 0 and NBSP, and the 0 0 1 1 0, and we're going to enter noth into the algorithm. Then as you see there, in iteration 1, we enter the first vector 1 - 1 - 2 - 1 0, we calculate the scalar products, we pivot, we put the second generator of S2, which is 0 0 1 1 0, and we pivot, so, you know that to get the subspace orthogonal to the subspace generated by those two vectors, what you have to do, is to eliminate the columns W, and the remaining columns, those that have the V, in green color, are those that generate the orthogonal subspace. Then the subspace orthogonal to S2 is the subspace generated by the three column vectors that appear in green color on the slide. Now the method tells us that we have to calculate the orthogonal to this subspace, in S1. So, look what you do in the algorithm, to determine this orthogonal subspace, not in the general space, but in subspace S1. For this, we simply start, instead of the unit matrix, with the generators of S1. Therefore, how are we going to calculate the orthogonal subspace? In subspace S1, we have to put the generators of S1, that is, the 1 0 minus 1 0 1, and 0 1 1 1 1. In iteration 1, as you can see, instead of the unit matrix, we have the set of generators of the subspace S1. Now we enter the three vectors that were in green previously, those three vectors, those who generated the orthogonal of S2. So, we enter the first vector, that is the 1 1 0 0 0, we calculate the scalar products, we pivot, we put the second vector, we calculate the scalar products, we see that we cannot pivot, because zeros appear in the scalar products, and therefore, in iteration 3, we copy the table from iteration 2, and we enter the third vector, the 0 0 0 0 1, we calculate the scalar products and we see that we cannot pivot, because the column V has scalar product 0, and the column that has W cannot be used, because we have used it before. In conclusion, the subspace we obtain is the one generated by the column in green color. Then the intersection of the subspaces S1 and S2 is the space generated by that column vector, as you have in the last row of the transparency. Let's put another example, so that things become more clear. In fact, it's going to be a repetition, but this way, we fix a little more our ideas. Now, we want to calculate the intersection of these subspaces S1 and S2, which are the same as the previous ones, and we are going to do it the other way. Instead of the second expression that we have given before to write the intersection of subspaces, we're going to use the third one. So, this expression that you have there, on line 3 of the transparency, is telling us that we have, first of all, to calculate the subspace orthogonal to subspace S1, for which we introduce in the algorithm the two vectors that generate subspace S1. The first is 1 0 minus 1 0 1, as shown in iteration 1, and the second is 0 1 1 1 1, in iteration 2. So, we simply apply the algorithm, we calculate the scalar products, we pivot and there's no problem, because we can pivot with first vector in column 1. Next, we enter the second vector and there is no problem, because we can pivot and we can even choose several columns to pivot. In this case we choose the second, and at the end, in green color, we have the columns that we have not used to pivot, which are precisely the generators of the subspace orthogonal to S1. Those vectors, the three vectors in green color, generate the subspace orthogonal to subspace S1. Then, the method tells us, looking at the third line, that we have to calculate the orthogonal to this subspace in S2, then, instead of starting from the unit matrix, as we always do in the algorithm, we start with the vectors that generate subspace S2 and, as you see in the second row of tables in the transparency, we enter them in the last part of transparency in the iteration 1, the vector 1 minus 1 minus 2 minus 1 0, and the vector 0 0 1 1 0, in iteration 2. Since we have to calculate the orthogonal to the subspace generated by those three vectors in green color, we enter those three vectors in the algorithm, and that's what we do. We enter the first vector in the iteration 1, we pivot, we enter the second vector in iteration 2, and also we want to pivot, but we cannot, because we find that, under the vector v1, a scalar product 0 appears. So, we enter the third, and it happens exactly the same, we cannot pivot. Therefore, we copy the same table in the final table. Now we remove the W column and we have only one V column. This means that the orthogonal we were looking for is the subspace generated by the vector in green. We can check that this vector is exactly the same as the one we had obtained with the other method. So, we have obtained the intersection of the subspaces S1 and S2, in two different ways, and we've seen that it gives the same subspace. I have to say that, sometimes, we do not get exactly the same generators. If it is a unique vector, it has to be a multiple, with a positive or negative factor, the other one, but if there are several vectors we might get the same subspace with a different basis, and then it is more difficult to check that they are the same, but it has to be the same, because otherwise it would be wrong.